Welcome. This is a presentation for our WACWI paper, BirdSAT, Cross-View Contrastive Masked Autoencoders for Bird Species Classification and Mapping. We are from the Multimodal Vision Research Laboratory in the Washington University in St. Louis. In this paper, we propose to learn a unified representation space useful for solving two tasks: species classification, which involves categorizing species with subtle differences into fine-grained classes, and species distribution mapping, which involves mapping the habitation of species of interest over any geographic region in the world. So on the left, you can see an example of the image from iNaturalist. So it shows the training locations and the validation and testing locations in the iNaturalist 2021 dataset. We specifically filtered the dataset to include bird species only. So as can be seen, the dataset includes a lot of rich metadata such as the geolocation of the observation, the year, the month, and the taxonomic information. So acquisition metadata such as when and where an image was captured provides additional context which can improve in interpreting the content of the image. Satellite images can also provide visual context of habitation of a species. So in this paper, we explore and evaluate early and late fusion style architectures to combine all the cross-view information available. So the contributions of our paper are threefold. We introduce a global cross-view iNaturalist 2021 birds dataset which contains paired satellite images and corresponding ground-level bird images. We propose a framework for cross-view pre-training of vision transformers along with metadata enabling the ecological mapping of bird species. We demonstrate the rich representational capability of our pre-trained models by demonstrating state-of-the-art performance on fine-grained bird classification across three datasets. So the cross-view iNaturalist birds dataset 2021 consists of ground-level bird images and satellite images along with metadata. In total, there are over 413,000 pairs for training and 14,000 pairs for validation and testing. The ground level images are of varying sizes while the satellite images are of size 256 by 256. The satellite images are Sentinel-2A. The first architecture that we propose is a unimodal style architecture with two objectives for training. They consist of modality specific vision transformer encoders and a vision transformer decoder for the ground level image. We use clip loss which aligns ground level and satellite images together along with metadata added to the satellite image, and we use the reconstruction loss that learns discriminative features from the ground level images. The second architecture that we propose is a multimodal style architecture with two objectives for training. It consists of a single vision transformer encoder and separate vision transformer decoders. We use the matching loss which matches multimodal representation along with metadata added to the CLS token. And we also use the reconstruction loss that learns discriminative features from the ground level and the satellite images. Here we show some examples of bird to satellite image retrieval. So the bird image is given as query and then we compute the similarity of the bird image with all of the satellite images in the validation dataset. So as can be seen, the satellite images are very similar to the habitation of species. We show some quantitative metrics that was used in our paper. The first table shows the performance of various models on fine-grained image classification on the iNaturalist 2021 dataset. As can be seen, our models outperform the state-of-the-art in both linear probing and fine-tuning. Next, we show some cross-modal retrieval metrics, which is satellite to bird image retrieval metrics. As can be seen, our model also outperforms the state-of-the-art MoCo V2 Geo model. The third table shows the performance of our models on transfer learning task on two datasets, the CUB dataset and the NA-BIRDS dataset. Again, our model outperforms the other models in both linear probing and fine-tuning. Here we show bird distribution maps generated using our models but without using any metadata. On the right, you can see the ground truth observations of the bird species present in the iNaturalist 2021 dataset. These maps are generated using the bird image to satellite image similarity scores. To conclude, we propose two architectures for fusing metadata, satellite image and ground level image for fine grained image classification. We systematically evaluated on the task of cross modal retrieval. In the future, we could combine information from other modalities such as text to improve the capabilities of our existing models. Thank you.